Okay. For this week and the next one, I want to sort of try and cover some kind of example applications of information theoretic and coding related ideas to computer science or to theoretical computer science in particular. I mean, yeah, this is only a small sampling, of course, and we won't, covering all of it would need more than a full course. Today, I'll sort of continue the discussion we had on Reed-Muller codes and just kind of briefly mention another form of decoding, which is useful in complexity and TCP-like applications. And then we'll start talking about communication complexity. I won't get to the information theoretic part of communication complexity today. I'll sort of cover that in the next lecture. Today, I'll sort of set up the model, have some discussion on what different things mean in communication complexity, etc. So we'll have a general discussion about the results and models, etc. All right, so let's start with Reed-Muller codes. If you remember, and this is how we defined that, and the star is sort of a reminder that this is actually a subcode of the Reed-Muller code. We defined it this way in the previous lecture that let's say you have a set H, which is a subset of field FQ, and you are now thinking of polynomials in M variables. Your given message corresponds to a function little h on this set h to the m. So you get these, if the set h is of size k, you get to write down these k to the m values, whatever you want. And then we find a polynomial such that its degree in each variable is at most k minus 1. And it kind of matches or sort of agrees with all the values we wrote down on this set h or h to the m. And we just kind of evaluate it on all points in FQ to the M and just write down all the evaluations. That's our code word. So we said that the dimension of our code was k to the M because we had this many degrees of freedom for choosing. And then, of course, the set of all functions is a linear subspace. So all functions on h to the M is a subspace. So this is a kind of yeah, this is a linear code, and we saw that. And the polynomials here that we wrote down were just kind of these indicator polynomials, similar to Lagrange interpolation. So this was just summation over so we have this kind of delta AI evaluated only on the variable xi, which is the same polynomial that came up in Lagrange interpolation of size k minus 1, or of degree k minus 1, sorry. And we just kind of multiply one such polynomial for every I, so we get degree k minus 1 in every variable. And we computed the distance of this code, which was related to the probability that a polynomial is not equal to 0, evaluated on a random collection of inputs from the field. And this in particular is the case where we had bounds on individual degrees, which we know are at most k minus 1 here. And then we saw that this was a bound on the fraction of points at which is non-zero. Okay. And the reason I defined Reed-Muller codes this way, rather than saying it's just the set of all polynomials in M variables with certain degrees. So you could think of the message either as the set of coefficients or the set of evaluations on a smaller subset of FQ to the M, which is H to the M. The nice thing is, if you think about the message in this way, that it's just evaluations on a subset of points, then you can ask the question, is it possible to just recover the message or sort of one bit of the message or one position of the message without recovering the entire code word? This is not quite true. You can't quite ask about evaluating one coefficient in the polynomial using in this language. But if you think of the message as sort of evaluations on subsets of points, then it's easy to do in Reed-Muller codes as we define them. And this is what is known as local decoding. So more formally, the question of local decoding is you want to recover one symbol of the message, or even kind of one symbol in the code word. Because the code word was just kind of evaluations on all of FQ to the M. The message was H to the M. So the message, like all symbols in the message are kind of form a subset of all the symbols in the code word. And if there was no corruption, you can just kind of read the message off directly by looking at the code. But now suppose there is corruption and you want to find still one symbol of the message or the code word in general. And we want to now find it in time, which is roughly what it takes to kind of write down the location of this symbol. So we want to find it in time, which is polynomial in M and the size of the field. If you had a polynomial time decoding algorithm for the code and you kind of decoded the whole code word, this would take time polynomial in the block length, or rather polynomial in Q to the M, which is the total number of evaluations we write down. So we want to do it much faster, but of course we sort of are not going to write down the entire code word. We don't quite have the time to do that even. So we are just going to find one one location of the code word or one location of the message. Is this okay? Okay. Still for a sort of after corruption. So of course, if there was no corruption, this is easy. You can just read it off. The question becomes interesting if there is some corruption. Another thing to note is this sort of, if we are allowing a constant fraction of the kind of symbols in the code word to be corrupted, which means that, let's say we are allowing 10% of the symbols to be corrupted. And this was what we were calling T. Then any algorithm you are using has to be randomized, because if it's a deterministic algorithm, there is no hope. The deterministic algorithm is going to query at most poly M and Q positions. And if you are if these are known ahead of time, the adversary can just corrupt the positions you are going to query. And so your algorithm for recovering a particular symbol, if the sort of set of queries is fixed and known in advance, the adversary will just corrupt them. This is much, much larger than the number of queries the algorithm is allowed. So this sort of means that the algorithm cannot declare all its queries in advance. And so we must have a randomized algorithm. This is a little different from how we defined encoders and decoders in the channel coding setting, where we were decoding the entire code, and there we could think of a sort of deterministic decoder, but here we need randomness. Any questions about this, about the task? Okay, so I'll not necessarily give the most general theorem of this type. I mean, there are lots of different parameter settings that are useful in different applications. Instead, rather, let me just give an example of a local decoding result with some parameters which illustrates the technique, at least in the case of large queues. So I'm going to think of it as, I mean, this is large, but it's still much, much smaller than N. So we are not in the Reed-Solomon kind of setting. N was Q to the M, and this is much, much smaller than that. It's sort of roughly kind of logarithmic or polylogarithmic in the block length, as opposed to N or sort of polynomial in the alphabet, or in the block length. But this is large enough that the kind of algorithm I'm going to describe can work, but this doesn't make sense when Q is 2 or 3, and there are local decoding algorithms there for certain for Reed-Muller codes. But of course, you need to change the definition of the code. You have to consider the full code rather than the subcode I considered, and you have to use slightly different arguments for. I mean, they're not completely unrelated, but you need to sort of state it or sort of analyze it somewhat differently. Okay, so let's look at this regime where we have this sort of moderately large Q. And an example of a theorem I want to consider is, let's say Q is sufficiently large, still much, much smaller than the block length. And then my claim is that, let's say if you have 10% of corruption, so you have a code word F, or sort of all the evaluations of F, it's corrupted in about 1/10 of the places, and you get F tilde. And now, based on F tilde, you want to recover F at any given position. So this is kind of more general than recovering one symbol of the message. Symbol lives inside F somewhere. In particular, you can choose the Z1 to Zm to be inside the set H, and you will recover the message, but this is more general. And the other thing is, you don't have time to read all of F tilde, right? So as we said earlier, the number of queries is, or the running time of this is much, much smaller than the block length. So we will use what's usually referred to as Oracle access or query access. Which just means that we will ask for, the algorithm will be able to ask for evaluation or F tilde at a given point, and it will be able to read sort of in some sort of a random access manner. So you can look at F tilde at any point you want. Okay? And we will look at a small number of points. Okay. Is the statement of the result clear before we proceed to the proof? Okay. And the generic idea in this decoding is just that if here I've kind of drawn some sort of cartoon picture of FQ squared. And in general, you can think of FQ to the M as this kind of large cube in M dimensions. And if you have a point, let's say here Z1, Z2, at which you are interested in sort of finding the value of F, and kind of green here indicates that the value is correct and it's not corrupted. The red indicates that the value is corrupted, let's say. So maybe it's, maybe we have that F of Z1, Z2 is corrupted. But if we look at kind of a random line passing through this point Z1, Z2, and we'll define a random line in a minute, but intuitively, kind of a random line, you can pick a direction and then just kind of walk along in that direction, and we'll do the finite field version of it. Then we can say that the kind of typical fraction of corrupted points along a line will be small, maybe 1/10, and then we will see. And we will be able to think of this m-variate polynomial as a univariate polynomial along the line, or a polynomial in a single variable. And if you have a polynomial in one variable in which you don't have too many corruptions, you can find the value at any given point using Reed-Solomon decoding. And that will be our algorithm. So let's make this precise. So let's say we kind of fix our target point, and let's keep it fixed throughout the argument. Okay. So Z is this kind of an input given to us. It's not going to change. And for any Y, you can think of this kind of line L sub Y, which connects Z and Y. And I'm just going to define this line as this set of Q points, which is Z plus U times Y, where U is between 0 and Q minus 1. So this is a set of Q points, which I'm just calling this line. Yeah, geometric intuition doesn't always translate correctly in finite fields, but okay. Any questions about the definition? Okay. And the next observation is that now let's fix both Z and Y. So we sort of Z was given to us. We picked a random Y and we fixed it. And now let's only think of u as varying. So we're just sort of looking at the q points on this line. And u is a single variable, and I can think of f as a polynomial in this one variable u once I have z and y fixed. So it's a polynomial in kind of now z1 plus u times y1, z2 plus u times y2, and so on. So there were m variables, each had degree at most k minus 1, and now each of these variables can be thought of as just kind of some shift of u. So the degree as a univariate polynomial in u of this function, and just along this line, is at most k minus 1 times m. Because each variable, each of the original variables now just becomes a copy of u of the subshifts. And so now, along this line, I have a polynomial in this one variable u. I'm interested in finding let's call this polynomial g. It's just a polynomial in one variable. And my claim is that kind of the desired answer is the polynomial g evaluated at u equals 0. I plug in u equals 0, I get f of z, which is what I really want. And now it's just sort of a little bit of kind of probabilistic bookkeeping that if I look at a random y and I look at a random line L sub y, then what is the fraction of points along this random line that are corrupted? The observation is that this is just a random point. For a fixed z, if I look at random u and random y, z plus u times y is just randomly distributed in f2 to the m. So, and the fraction of corruptions overall on average is 1/10. So the expectation of this probability along a random line is 1/10. And then by Markov's inequality, the probability that for a random y, the line in direction y has more than 2/5 of the kind of values corrupted is at most 1/4. It's just just Markov's inequality. So about 3/4 of the lines are pretty good in the sense that the amount of corruption in this line is is at most 40% or at most 2/5, and at least 3/5 of the values are good. Okay. So now once we kind of fix a good line, and now our goal is find this polynomial g, let's say, and then evaluate it at 0, where g of u is this polynomial corresponding to f of L y evaluated at u. Given less than equal to 40% corruption. And this is just a question of decoding Reed-Solomon codes, because Reed-Solomon codes correspond to evaluations of a univariate polynomial. Here, the number of evaluations is q. So my claim is this is a Reed-Solomon code with q evaluations. the degree, which is and Q is by design greater than or equal to 5 km. So you can check that this is the amount of errors we can handle is less than the threshold Q minus so the number of errors is less than the threshold at which we can do unique decoding. I mean, I think the parameters work out. If not, just increase Q a little bit more. It's just a question of changing it from 5 km to 10 km if you really need to. Okay. So then here is our algorithm that given Z1 to Zm, where we want to find the value of this function f, we don't sort of the value at this point, or the written value in f tilde here might be corrupted, but what we are going to do is pick a random direction y, and this gives us a good line Ly with probability 3/4, and a good line has a small number of errors, at most 2q/5. So the goal is to find a univariate polynomial which agrees, or which has errors at most 2q/5 compared to f tilde. And this is just Reed-Solomon decoding, unique decoding, and then we output G0. And this algorithm succeeds as long as the line is good, so it succeeds with probability at least 3/4. And you want to boost the probability, you can just repeat this a few times and yeah, sort of output the value which occurs the largest number of times. There are many standard ways to boost this probability. Okay. And this is quite useful in constructions of probabilistically checkable proofs, or using codes for what's called hardness amplification, where you want to think of the code as kind of describing the truth table or evaluation table of an NP language, and sort of what you are interested in is kind of evaluating the output of a Turing machine or language at one point, and then you just think of the entire truth table as a one big code word. So in those kind of settings, and local decoding makes much more sense, and Reed-Solomon codes can be sort of easily sort of locally decoded, basically because on a line they look like Reed-Solomon. And this is also the reason we defined them in the slightly funky way that you define the message on a set of points and then extend it everywhere else. Okay. Any questions about this? We'll switch topics now. Okay, so the next topic I want to discuss for the rest of this lecture and the next lecture is communication complexity. This is one of the areas where information theory or information theoretic ideas have been quite useful. And today I'll mostly spend the lecture sort of describing the setup and many variants of communication complexity, or many different setups here. And then we'll get to the information theoretic notions in the next lecture. The goal in many of these settings is to compute a function which, let's say, has two inputs, and let's say both of these are n-bit strings. I mean, in general, they can come from two different universes, X and Y. Instead of two inputs, they can be many different inputs, and they can be distributed between different parties in kind of many ways. But let's say we think of the two-party version of communication complexity for now. And here, I guess since times immemorial, the two parties are called Alice and Bob. So we'll stick to that. And let's say one input is sent to Alice, one input is sent to Bob, and their goal is to potentially exchange information and sort of figure out the value of f. They each know one of the inputs, and they will exchange information according to something we'll call a communication protocol. We'll sort of state more formally what it is, but they want to exchange enough information to compute f. And we will try to use various techniques, also in particular information theory, to try and sort of understand how much information do they really need to exchange. And it's something which depends on this function f, and we'll see that the answer can be very different for different functions f. And a couple of things to emphasize. So usually in information theory, we were kind of saying, we know what message we want to send back and forth, and just can you give me the best way of sending it? Can you compress it as much as possible? Can you protect it against errors or whatever? Here the setting is a little different. So we don't sort of quite know what's the best protocol or what's the best message to send. And not necessarily, like, we don't even necessarily want to think about all possible kinds of messages that we could have sent, but we want to say that sort of we want to prove maybe lower bounds here, that no matter how you try to exchange messages, because of the very nature of the function f, you need to at least exchange so much information. So not surprisingly, these quantities is referred to as the communication complexity of the function f, and there are other things which are called the information complexity of function f, maybe function f and a protocol, and like, so there are various versions, but you think of them as properties of this function, and maybe some other things in the setup. Okay. Any questions about the model? Okay. And let me just add that this itself is an abstraction which is kind of useful in many other settings. So if you have, let's say, a streaming protocol, and let's say you're kind of reading data which is coming across in a stream, and you have some sort of bounded memory device which is sort of sitting and looking at this stream, and you are interested in understanding how much memory do you need to compute some properties of the stream. You can think of, you can break the stream into two parts, the first half of all the inputs that came in the stream, and the second half. And let's see what is stored in this memory after the first half of the stream is done and the second half is yet to come. It's something which you can think of as communication from the first half to the second half. So at the end, you're interested in computing some function of the entire stream. And if the memory is only sort of k bits, it means that sort of the first half of the input only communicates with the second half through k bits of kind of memory, or k bits of information. And so you can only hope to compute functions which you can compute with k bits of communication. Similarly, you can think of data structures where you have a lot of information stored, and you can think of appropriately maybe as some sort of parts of an input. And when you query the data structure, you can think of that as communication. So the kind of abstract setting of communication complexity also comes up in a lot of other applications, which can be modeled after some kind of massaging as a communication complexity problem. But we'll, at least for now, focus on this abstract communication complexity setup and just try to understand how much information we need as a function of what we want to compute. Right. And information theory really shows up when you kind of introduce randomness into the problem, but it's easier to understand all the objects when we don't have randomness. So let's start there, and then we'll slowly kind of introduce randomness into the setup and see what we want to understand. Okay. So in the deterministic setting, the two inputs x and y are arbitrary. Alice has x, Bob has y, and they're interested in computing f of x, comma y for an arbitrary X, Y, or rather they need to have some way of exchanging information which correctly computes this function on all inputs, okay, whatever protocol they have for exchanging. And pi we will define as a protocol, but when we say pi computes f, we sometimes also think of as just write the notation pi of x comma y, which is whatever pi computes on these inputs. And what we'll see what it means to say pi computes something. Another way of writing this is pi of xy is equal to f of xy for all x. And the communication complexity of pi on f is just maximum over the kind of input pairs, number of bits exchanged in the communication. Okay. And now let's define this protocol more carefully. So what we mean by protocol is that Alice and Bob have some way of talking to each other. So they will both receive an input, and let's say they both receive the input simultaneously. Once they receive the input, they know that it's time to start talking. And at any given point, like, so they've previously maybe met and agreed on how they are going to talk. They don't know their inputs, but what I mean by how is that they have agreed sort of that they know at any given point who's going to speak next. And when I say any given point, it's a function of the kind of messages they've exchanged so far. So they started talking, maybe it's the kind of the turn for sending the third message, and the previous two messages have been 0 and 0. So at this point, maybe according to their protocol, they know that Alice should speak next. Okay. So it's a function of, so who speaks next is a function of what time it is and sort of what has been said so far. It's not a function of their inputs right now, because I mean, it's a function of their inputs, or it depends on their inputs in some sense, because the previous communication depends on their inputs. But given the previous communication, it doesn't depend on the inputs anymore, because the rest of the stuff is only known to one of them. And sort of, we want them to be in agreement about who should speak next, based on what they've exchanged so far, which is visible to both of them. Okay. And if they know that at the next time kind of Alice is going to speak or Bob is going to speak, then we can say that what Alice will say is kind of known as a function A, which depends on the previous communication and can depend on Alice's input. Okay. You can think of it as a function of two inputs if you want. I'm just sort of writing it this way because it will be easier in a minute. And if Bob is going to speak, then Bob knows what he's going to speak as a function of the input he received and the previous communication so far. And we will kind of restrict that whoever speaks last has to speak f of x, so f of x comma y. So the last message should be whatever they think is the value of f of x comma y, because we are interested in protocols which always correctly compute. I mean, in general, we'll just call the last message as, we'll define it to be pi of x comma y, and we are just saying that we are looking at protocols where the last message is always correct, the correct value. And we are assuming that kind of at any point in time, only one bit is spoken. We don't care about time so much as the number of bits. I mean, it's fine if Alice wants to sort of say a lot. It's just that at time 1, she'll say 1 bit. At time 2, she'll say another bit, and so on. Same for Bob. So as long as they know who's going to go next, it doesn't matter if we kind of break their speech into 1 bit at a time. Any questions about the definition of what a protocol is, or what it means to sort of have an agreement on how to communicate? A nice way of thinking about it is in terms of binary trees. So we will think of every node of this binary tree as defining the amount or like the content of the communication so far. Okay, so each node defines the at any given point, the next sort of bit of communication is either 0 or 1. So we have each node has 2 children. And we can keep writing down this. We can, I mean, yeah, need not be balanced. So maybe after some 3 bits, they decide that they already figured out the value of the function, but in some cases, it might take them 5 bits. So it's not necessarily a balanced tree. And what we said can be written in the form that each node V is labeled by a function a sub v of x or b sub v of y. So it's a function which either kind of says that Alice is supposed to speak, and this is a function which depends on the previous input and on Alice's input, or it's labeled by b sub y. And so a protocol can be thought of as a deterministic protocol can be thought of as this kind of a tree. And the communication complexity is the maximum depth of a path in the tree. So these are equivalent ways of thinking about deterministic communication. It's kind of sort of convenient to think in this tree form or this binary form because you can use various inductive arguments, sort of given what you know so far. At the next step, there are only 2 things to argue about. And that usually helps a lot in reasoning about the protocols. Okay, any questions about the model? Okay, and now we are interested in sort of understanding how the amount of communication depends on the function. So let's do a couple of examples. And this also introduces some functions which are quite common or play a role in this. First claim is that you can compute any function whatsoever with n plus 1 bits of communication. Okay. Any guesses why? Anybody still online? Okay, let's hope people are still online. But
you need to read the input and output the final bit, right?
Yeah. So I mean, not just read, but they can send the input. So so here's the protocol that kind of let's say Alice sends X to Bob. This takes n bits, and Bob outputs f of x go y. So Alice sent n bits, and then Bob sent 1 bit, or the other way around. This is asymmetric. You can define it in either way. But the important thing is we are not measuring how difficult it is to compute f of x comma y if you know both x and y. F of x comma y might be a very difficult function to compute, but we're not charging for that. The only question is how long, like how much communication do we need between Alice and Bob? Okay, and one of them can always send their input to the other. That's the only piece of information the other is missing. So after n bits of communication, one of the 2 parties will have everything they need to compute the function, and they'll just use 1 more bit to write down the value or the output. Okay. So this kind of says that anything we are like n is trivial, basically, or n plus 1, and we'll be interested in asymptotic bounds. So it's more interesting to see sort of how much smaller or larger, how much smaller than n is the communication complexity for some given function. Now, another function which maybe an interesting example to consider is kind of, it's just bitwise sums modulo 2, and then you sum the whole thing. So you look at x1 plus y1 modulo 2, or XOR if you like, x2 plus y2, and so on, and then you sum all of them together. Okay? All of this is modulo 2, so you get a 1-bit output, and that's the function. And my claim is that the communication complexity for this function is very low. Anyone wants to kind of guess or tell me how much it is?
It's 2, right?
Yeah, so you can do it with 2 bits because let's say, so I'm kind of starting with protocols where Alice starts the communication, because Alice and Bob's kind of nice to go in that order, but yeah, you can start either way. But Alice can send and then, so this is 1 bit, let's call it B, or actually let's call it A, since Alice sent it. And then Bob computes y1 to yn, which he already knows, plus A, 1, 2, and then sends that back, that is equal to the value. So because you can kind of rearrange these brackets in any way, you can, and so addition is both commutative and kind of associative, etc. You can just think of x1 plus x2 to xn, and then y1 plus y2 to yn. The third is what is called the inner product function, where now instead of taking the bitwise sum of x1, y1, I'm taking the bitwise product. So product of 2 0 1 numbers is just a and then I'm adding them up. This is a somewhat more involved function. It's usually called the inner product function, although it's a dot product over a finite field. It's not really an inner product, but here, I mean, yeah, it's requires a bit of a proof, but of course we can compute this function with n plus 1 bits like before, and we will be able to kind of also argue that you actually need a lot of bits of communication to compute this. Okay. Similarly, for these other functions, which are also important, and these are the two we'll be mostly following as we look at different models of communication. First is called the equality function, where we are given 2 strings. We want to just check they're equal in every position. So each xi is equal to yi. And the other is called the disjointness function, which usually think of x1 to xn if you think of as a string of n bits, you want to think of it as maybe, let's say, a subset of 1 to n, which is just whatever bits are 1, you think of as a subset. And the function is really saying that x and y together form disjoint subsets. So for every position I, and the ith element is either not present in x or not present in y. It can't be present in both of them, because then it would form an intersection and you would not have disjoint subsets. Okay. So, and disjointness is kind of the prototypical problem. Like a lot of the lower bounds, even for very strong models of communication, are proof for disjointness, and we will talk about information theoretic proofs about disjointness. Any guesses or suggestions as to what their communication complexities might be? Well, disjointness maybe already said. What about equality? You don't have to prove it, but just if you have a guess.
It should be hard, like n, like order n.
Okay. I mean, intuitively, it seems like, yeah, for equality, because somehow, if you were thinking of communicating bits of X themselves, then of course you have to communicate all bits, because I could change one of them, and so if you didn't send me all the bits, I can just change Y in one position which you did not send me. But I mean, remember that the protocol is not just sending bits of X and Y. It's allowed to compute any functions, sort of these functions A sub V at X and B sub V at Y. And so it could send whatever it wants. And we need to argue against all of these things. And for equality, it turns out, for both of them, it turns out that the communication you need in the deterministic setting is large. But for equality, it will turn out that if you have randomness, you can actually reduce the amount of communication quite a bit. For disjointness, it doesn't seem to have. Well, it cannot. Okay. So, and we'll see sort of these things in a bit, but right now I'm just stating known results. I'm not proving things. Okay. Okay. One other useful tool to sort of understand communication complexity is to think of this kind of giant 2 to the n plus 2 to the n matrix, where you have one row and one column for every kind of string. So for every x y pair, you have a row column pair, which gives you an index x comma y, and there you've just written down the value of x comma y. So this is a matrix in which entries are 0 or 1, and the dimensions are 2 to the n plus 2 to the n. And a very useful thing about this matrix, which comes out of deterministic protocols, and then this has generalizations for randomized protocols, is that a deterministic protocol defines what is called a rectangle. So a rectangle is just a submatrix of this. So a rectangle is just specified by an S, which is a subset of rows, a T, which is a subset of columns. And you think of this matrix M sub S, which is just all x comma y, such that x is in S, y is in T. So it's just this submatrix. It's not necessarily a square submatrix, not necessarily a principal submatrix, but some submatrix. And the claim is that every single node in this protocol tree actually identifies a rectangle inside this matrix, and in fact leaves kind of identify disjoint rectangles. And they partition this matrix when you get to the leaves of this protocol tree. So and this will be very useful in terms of understanding protocols, because instead of understanding protocols directly, we will be able to understand partitions of this matrix into rectangles. And that will allow some sort of linear algebraic methods or methods related to distributions, etc. Okay. Any questions about the claim? We'll prove it in a minute, but okay. All right. And okay, the claim is trivially true at the root, because there we are talking of the entire matrix, or let's say we just declare that we are talking of the entire matrix. And now let's suppose we are at this node V. We are looking at a rectangle S sub V cross P sub V. And let's say it's labeled with some function where Alice is supposed to speak as a function of the input. Now there are two ways things can go here. Either this function is 1, so we kind of go down on the left half. Or let's say 0 on the left. And I claim now we can think of all the inputs which are sort of consistent with this node as follows. So look at all the inputs which could have led you to the predecessor of the node S sub v. And I claim that if you look at all points where A sub v is 0, and then keep the set of y's the same. Similarly, here you can think of all inputs which led you to the parent node and restrict to all inputs where so what do I mean by each node identifies a combinatorial rectangle? I guess I should have said it more carefully, that this node is reached if and only if the input xy belongs to this rectangle identified by this node. Okay, let's call it. And the root is always reached, so I identified the root with everything. And then I claimed that if any node identifies a rectangle, then 2 of its children also identify a rectangle. So by induction, we are done. It also proves that the leaves identify disjoint rectangles, because for any pair of inputs x and y, you reach exactly one leaf. And so it means that the leaves identify disjoint rectangles which partition all set of inputs. Okay. So okay, any questions about this characterization of the protocol trees? So we've come up with sort of maybe a couple of different ways of thinking about a protocol as a sequence of instructions, as these kind of labeled binary trees, as partitions of a matrix, and that sort of each of them are useful in just trying to understand upper or lower bounds on communication complexity. A very basic bound that comes out of this characterization is called rectangle bound. So we said that if you have a tree, then the leaves of it partition the rectangle, the matrix into rectangles. And there is one very important property, which is that the value of the function is just determined by what's written at the leaf, right? So the function is constant on rectangle at this leaf, because once you are down at the leaf, the protocol has one fixed value which it outputs. We know it always correctly computes the function, so the function must be constant on every leaf of the rectangle identified by every leaf of this tree. Okay, and so these are called monochromatic rectangles, or function rectangles where f is constant. Okay. So any questions about this? So these are sometimes called f monochromatic, where we think of 0 and 1 as two different colors, and hence monochromatic. It's either all 0 or all 1. Okay. And this, for example, can give us a bound on, let's say, the communication complexity of the equality function. So let's see what the matrix looks like for equality. Because so the x, yth entry should be equal to f of x comma y. This matrix should be the identity matrix because if the function is only 1 when x is equal to y and 0 everywhere else. And now we can say that the number of leaves in our tree must be greater than equal to number of monochromatic rectangles needed for partition. And on this matrix, no two of the ones can be in the same rectangle, because if you had a rectangle which included two of these ones, because we have to be constant, this entry will also have to be 1, which is not allowed. These entries have to be 0. So no two ones can belong to the same monochromatic rectangle. And so for the equality function in particular, the number of rectangles is at least 2 to the n plus at least one more, because this covers all the ones, and maybe you need at least one to cover all the zeros. Actually, we'll need more than one, but it's fine. So if you have a binary tree that the number of leaves is more than 2 to the n plus 1, then the depth of this tree is greater than equal to log of the number of leaves. And so the depth is greater than n. So we need well, at least n plus 1 bits of communication. Any questions? This is just a lower bound on the deterministic communication complexity of equality. This is perhaps one of the simplest bounds, and you need slightly more sophisticated techniques for other functions. But this is just to get used to deterministic protocols. Okay. Any questions? Otherwise, we'll switch to randomized ones. And like I said, we'll kind of see information theory next time once we set up randomized protocols. So I also wanted to just develop all the notions that we get on our way to randomized protocols. Okay. In randomized ways, I mean, there are at least 3 ways we can think of randomness or introducing randomness into the problem, and then let's see them one by one. The first is the input is arbitrary. So x and y is still arbitrary. And Alice and Bob can use randomness in computing their functions. What this means is that the function at any given node can now depend on the input and the randomness that is available to, let's say, Bob, because this node is labeled. And if this node was labeled with Alice, then we can have a sub v of x, and so on. So let's call this node u. So these functions now are not just functions of the input, but they can be labeled with randomness. That's one way of thinking about it. Going to rectangles and so on gets slightly more involved, but we'll get there in a bit. Any questions about the notion of randomness we are talking about? So it's very important here that they are still required to compute x and y on every input x comma y. But now the problem is that the path they will follow on this tree doesn't just depend on x and y, but it also depends on what random bits they had. And we can think of r sub a and r sub b as a finite length sequence of bits. and they just kind of tossed some random coins and then just kept the outputs for themselves, and then they're computing these functions. And we'll define the communication complexity, or the randomized communication complexity with error epsilon, is as the minimum communication complexity on any protocol, which is again this kind of a label tree if you want, such that for every input the protocol computes f correctly with probability at least 1 minus epsilon. Okay. And I mean, all the action you can think of is the constant epsilon, you can boost it without too much work. So although there are some subtleties, but let's say we think of just epsilon as 1/3. So we just want to compute the value of the function correctly on every input with probability at least 2/3. And now I claim that, let's say if you were still interested in equalities x equal to y, then the amount of communication you need is really small. In particular, you can handle log n, you can work with log n bits of communication. And it might be easier to start with this simple case where I tell you something more, that either x is equal to y or they differ in at least 1/10 of the positions. So either they are exactly equal or they're very different. So we can't just have this kind of tiny case where we changed y in one position. Now, any guesses for how to communicate just a little bit if you have randomness?
You generate a random index and share that index and value.
Okay, so you generate random I, and then sort of send I and send, let's say X or Y, let's say LS is sending this. I mean, yeah, I think all the settings we'll talk about, kind of the roles of Alice and Bob are symmetric, although there are some communication questions, especially something called indexing, where the input lengths are different, and so their roles are a bit asymmetric. But let's say for now we just think of symmetric roles. So then Alice could sample a random index, send the location and the value of X in that location. Bob kind of checks if yi is equal to xi. And if x is equal to y, then they will sort of, this will be, the answer will be yes with probability 1. And if a is sort of, if they are far apart, then the answer will be kind of no with probability at least 1/10. So the correct answer in this case with probability at least 1/10. Or the answer will be yes with probability at most 9/10. And because we want to sort of succeed with probability at least 2/3, we'll just sort of repeat this a few times. So let's say I want ik, and then we will send I1 to ik, xi1 to xik. Bob will check the same sort of, and the probability that the two strings are not equal, but then they end up being equal in each of these positions is at most 9/10 to the k. So you can choose k to be some small constant, I mean, and maybe 10 or 11 should suffice, such that the probability of accepting becomes less than 1/3. So in this case, they will reject with the probability at least 2/3, which is great. So they'll compute the correct function. Okay. Now, of course, we want to compute x and y for, or like this equality for all x and y, not just this special case. Okay. So let's say we want a transformation such that we kind of map x to phi of x and y to phi of y, such that if x is not equal to y, then phi of x and phi of y are very far. Let's say the length of these is n prime. Then if x is equal to y, then they're equal. What is such a transformation called? It has a name which we all know. Okay, it's called a code. See, in a code, that's exactly what we do. We sort of encode messages. I think of x and y as messages, and such that the encodings for any two messages or any two code words are at a large distance from each other, unless they're equal, in which case, like this, because the mapping is a function, if you map, if you compute it on x twice, you will get the same answer. So just use a good code and then do the same thing. Okay, any questions? So you can check, for example, you can do this with as an example, try doing this with Reed-Solomon code. Think of x and y as specifying coefficients of a degree n-1 polynomial. And then use a Reed-Solomon code and see what happens when you try to try to test evaluations at a few points. Okay. Any questions? Okay, so here we know that equality, for example, we saw that in the deterministic setting, we needed at least n bits of communication. And if we allowed this kind of random bits for x and y, for Alice and Bob, then log n bits of communication sufficed. And there are a couple other ways of thinking about randomness. So, and some of these are easier to think about when designing protocols. Some of these are easier to think about when proving lower bounds. But another setting is where you allow Alice and Bob to use randomness, but the randomness is public. So instead of Alice having R sub A, Bob having R sub B, they both have a random string R. And now they can do whatever they want. Sort of everything is still a function of x, y, and these random bits. But now there is a nicer way to think about these trees. You can say that for every fixed value of R, there is a single tree. And this couldn't be done before, because in these trees, at some places R sub A appeared, some places R sub B appears, but now that's not the case. So so we get a kind of deterministic protocol. For each fixed R. So yeah, we can again kind of define what is the kind of randomized communication complexity. We still want to compute the function f at every input with probability maybe 1 minus epsilon. So this is still arbitrary. But now my claim is that, okay, this is called R epsilon with public coins, communication complexity of a function, let's see. And my claim is that now it's actually constant. You don't even need to send log n bits of communication, but you can send a constant number of bits of communication. And it's just like you stare at the previous protocol, you send two things, the indices and the values at those indices. And if you are allowed to use shared randomness, then the indices can be simultaneously known to both Alice and Bob. So and the only part that you need to send, which depends on your input, is just the bits xi on those indices, which is just constant because these are doing constant number of indices. So you can do a bit better here. Okay, is that here? It's just a slightly different randomness model. And it's slightly convenient to think about because you can always do this sort of fix an R and then analyze as a deterministic protocol. And this turns out to be quite useful. Sorry, go on.
Just a question. So for the previous algorithm, let's say I didn't want to use this code to amplify this.
Okay.
Is there like some, can I do something like a binary search where I want to like search for the first index at which they differ? Or like, I just want to search for the first index where, you know, xi has a 1 and yi is 0. And
okay.
Like, it might be like log square and like maybe
the issue is, how do you say that do they differ in the first n over 2 indices? So you're going to run an equality protocol on the first n over 2 indices, and you're going to run an equality protocol on the last n over 2 indices, right? So and so naively, this recursion seems like T of n is equal to 2 times T of n over 2. And that will have linear cost. Like if you're not processing, if you're just searching for the first bit where they differ, they can of course differ in exactly one bit. And binary search will have to say, do they differ in the first half or do they differ in the second half? Which are just two smaller instances of equality.
Yeah, but now if I do something like I can first share how many ones are there in the string, right? And then I want to like share the position of the ones, right? Like where is like the k by second n, k by like is there k1, which is where is the k by 2th one, and then if that is, I mean, I'm not sure as vaguely thinking.
We can think about it offline. I mean, we can talk about it after class and see what other protocols. So, I mean, I would think that any of these protocols are implicitly defining a code, because what they are saying is that you are able to kind of locate, like instead of the difference being in one small place, the difference becomes very visible with sort of few easy queries. And intuitively, I think of this as something which amplifies the difference. But we'll talk about it after the lecture, and we can see what exactly is the protocol. But that's the number of ones thing you are describing is not binary search, right? Then it's something else. Okay, so let me just say sort of the relation between these two settings. So first, you don't need to communicate more using shared randomness, like the sort of communication complexity with public randomness is at most the communication complexity with private randomness. Okay. And this is just because, I mean, they can have shared randomness, but they can just agree that they will never read each other's parts. So they can just partition their shared randomness into two parts and proceed as if these were private to them and run whatever protocol they had. And so you can simulate any private randomness protocol using public randomness. Very interestingly, you can also kind of go in the other direction up to an additive log n loss in the amount of information or the amount of communication. And we saw that this log n is kind of typed in the case of equality. So, but roughly what happens in equality is typed. You don't really need to suffer more than that. And if you are shooting for an omega n bound or omega square root n bound, this log n is just additive, not even multiplicative log n. So in many cases, you can work with either, and it doesn't really change the complexity that you're going to get. Okay. We'll prove this in a minute, but any questions about these statements?
I have a question. Does it matter how many random bits we're having?
Right. So it does, and in some sense, the first step of this proof is to say that you can always assume you're not using too many random bits. You can always bring down the number of random bits without changing the probability epsilon by more than some small additive factor. So that is, in fact, one of the first things we will argue. But in some sense, without loss of generality, we don't really need to use a lot of randomness if we are willing to change the epsilon a little. Other questions? We'll argue that in a minute. Okay. So what are we interested in doing? We have public coin protocol, which potentially uses a lot of randomness or shared randomness. And we are interested in designing sort of a private coin protocol, which doesn't use as much, doesn't use much more communication. And the first step is that if R was kind of only belonging to a small set, so if there are only one of T random strings that they were using, then can simulate this protocol, let's say epsilon prime f is less than equal to epsilon prime. So if some protocol with epsilon prime error was only using one of T random strings, or rather I should have just written it about the communication complexity, but then I just need an additional log T factor. Okay. And this is because Alice can sample a number between 1 and T and send that number to Bob. And now they both know which random string they're talking about out of these 1 to T strings, and they're good to go. So they both know this shared randomness, and they can run their sort of public coin protocol. Okay. And the next part, maybe I'll ask you to think about, and then we'll do this next time, is that if you just kind of randomly sample, so if you randomly sample R1 to RT from whatever length strings are being used in the protocol, then T, which is maybe n over delta square, is enough. Okay, so instead of whatever length strings are being actually used in the protocol, just change the protocol to use one of R1 to RT, where R1 to RT are just chosen randomly. And this only changes the error probability by an additive delta. So you will go from a public coin protocol with error epsilon to public coin with epsilon plus delta. And then once we can get to this setup, we will just use the previous argument to go to a private coin protocol with an additional log T. So this is nothing complicated, just Chernoff bound, but I can do this in the next lecture. Okay? I'll ask you to think about it. And next time we'll talk more about information theoretic applications or applications of information theory. Okay. Any other questions?